Hello and welcome to our presentation for Lab 3. This is Group 7, consisting of Alexander Farrell, David Durant, and Christopher Barr. The thesis for our presentation of this lab is to create a digital design solution for real-world problems using Karnaugh maps, Boolean equations, CAD programs such as Logisim, and creating gates and logic devices. The purpose of this lab is to design and implement a circuit consisting of 4 inputs and 4 outputs. Successfully derive a Boolean equation from a truth table using Boolean algebra and K-maps, implement the simplified equation using a digital simulation program using gates, and to implement the simplified equation using a digital simulation program and a programmable logic device. We will explore how we fulfill this purpose through this lab. So how will we accomplish this? For this lab, we will fulfill this purpose by designing a circuit to control brake lights and turn signals. We use this as an example of how digital design solutions can solve real-world problems. Let's explore the inputs which make the brake lights and turn signals work. Our inputs are the left turn signal, the right turn signal, when the brakes are applied, and we also add a clock as an input which will allow the turn signals to blink. Specifically, our outputs are the left front light, left back light, and right back light. Let's get into the specific steps to solve the problem. We will start with Karnaugh maps, move on to the Boolean equations, describe our CAD program, and then explore the gates on the actual circuit and how everything is wired up. We will also explore an alternate solution using read-only memory instead of gates. Each output has its own Karnaugh map, and in this case, each output is one of the lights on the car. We use Karnaugh maps to simplify the circuits by eliminating wiring and gates that are redundant. Each one of the loops you see here tells us which inputs we need to connect to the outputs and allows us to make our design more efficient. From the Karnaugh map, we can figure out the Boolean equations. Variables multiplied together must both be true. Inputs added together must either have one or the other true for the output to be true, and an apostrophe mark denotes the complement of a variable. These equations are simplified by the Karnaugh map so that we know exactly how to wire everything up efficiently and correctly. We will be using the CAD program Logisim to simulate our digital circuit. We can directly translate the Boolean equation to the actual circuitry. Anytime we need to multiply two variables together, we use an AND gate. Anytime we need to get the opposite of something, we use a NOT gate. And anytime we need to add the result together, we use an OR gate. While this may look complicated, each one of these circuits is just a step in solving the equation, similar to how you would in algebra. Eventually, the wiring gets to the outputs, and we can get the state of whether each light is on or off by the value of each output. We have labeled each variable for clarity. We can also save the state of each possible combination of inputs and what the outputs should be. We do this through read-only memory, which is an alternate way to solve our problem that does not require the same logical process or Boolean reduction. Notice how we've replaced the gates from before with read-only memory completely. As the inputs change, it will access the combination of inputs, which are currently true, and then return the output to the lights. In conclusion, we have demonstrated very powerful tools in solving real-world problems using digital design solutions. We use these circuits every day in virtually every facet of our lives. We've also demonstrated that there are alternate options for solving the same problem. And using these steps increases design efficiency. Lessons in efficiency can be taken from this process and applied to improve many other things, such as the workflow of an employee. This is the end of our presentation. We appreciate your time and look forward to your feedback. Thank you.